Hello, I'm Sándor Bugyo. If you're interested in truly great mysteries, then this video is perfect for you. You can find solutions to many interesting problems here. The double-slit experiments, quantum measurement, motion and time, extra dimension and wormhole, quantum entanglement, faster than light communication, the origin of the unknown attractive force attributed to dark matter, and some more. First, let me introduce the double-slit experiment. You may have already heard about it. Richard Feynman, the Nobel Prize-winning physicist, said that this experiment encompasses all the truly puzzling and bizarre aspects of quantum physics. Let's see what it looks like and then explore its different versions. As we know in the Macroworld, if we cut two slits in a piece of paper and let sunlight pass through them, we will see two bright stripes on the screen behind it. Nothing surprising there. But what happens if we shine a laser through two needle-sized holes? I pierced a plastic card with two needles. If you are not familiar with the experiment, you might expect to see two green spots as a result. However, surprisingly, we don't get two spots, but a striped pattern. This is called an interference pattern because it usually occurs when waves collide. To illustrate this, I found an excellent simulation online created by the University of Colorado. I want to express my gratitude to them for making it available. First, we see that when we generate waves from two sources in a pool, the waves cause interference. When a wave crest meets another wave crest, they reinforce each other. If a wave trough meets another wave trough, the result is also a trough. Finally, when a wave trough meets a wave crest, they cancel each other out. Now let's look at the simulation when the waves pass through two slits. Similarly to the previous experiment, we obtain an interference pattern. If we bring the slits closer to the screen, we get the familiar two stripes in the Macroworld. And when we fuse the slits, there will only be one stripe as the result. Lastly, let's take a look at the simulation of the double-slit experiment with light. Above, you can see the laser source, the slits, and the screen. Below, it's magnified. As soon as we press the button, these slanted stripes appear, clearly demonstrating interference. By changing the color of the light, we alter the wavelength, and thus the resulting pattern. In the case of a single slit, we can choose to use a circular or square-shaped opening. We will go deeper into the explanation later. On the next slide, we see what happens when we perform the experiment with electrons. While we can imagine light as composed of some kind of waves, like waves on water, we tend to think of electrons more as tiny tennis balls. The electron gun shoots out electrons one by one, with intervals between the shots. This way, the electrons don't have a chance to influence each other. Each electron can only pass through one of the slits, and when it finally hits the screen, we get just a single point, not some kind of wave. What do you think the result will be? An interference pattern or two stripes? If we shoot out a large number of electrons, an interference pattern emerges. The other figure shows the result of an actual experiment. The first image shows fewer electrons, and then more and more are shot out. In the last image, the developed interference pattern becomes strikingly visible. I believe this surprises many people. The surprise becomes even greater when we discover that it works not only with electrons but also with so-called buckyballs, where 60 carbon atoms form a Bohr-shaped molecule. Moreover, in 2019, it was successfully demonstrated with molecules consisting of 2,000 atoms. While no one disputes that it works this way, the interpretation of the experiment divides physicists. On this slide, we take a peek and observe which slit the electron passes through. What kind of pattern do you think we will get? An interference pattern or not? Let me give you a moment to think. The result was very surprising to me. The interference disappears and we get two stripe patterns. Many physicists explain and teach the phenomenon with the interaction between particles or the effect of the measuring device. We will see that this is not the case. Below I present a homemade version of this experiment where I perform it not with electrons but with photons. I shoot a laser beam through the two slits, but this time I cover the right one with a vertical polarizer and the left one with a horizontal polarizer. As we know, when we stack a vertical and a horizontal polarizer, they block the passage of light. Therefore, when the photon hits the screen and we measure its polarization, we can determine which slit it passed through. In other words, the path information becomes known. If we measure vertical polarization, it obviously passed through the right slit, and if we measure horizontal polarization, it passed through the left one. As you can see, there are no slanted stripes. The interference pattern disappears. In the case of light, we don't get two different spots, only a single big one. Let's take it even further. Suppose we peak, but then we erase the result of our peak a little later. Once again, you would have to guess what kind of pattern will appear as a result. I give you some time to think about it. Well, the mind-boggling, mind-blowing result is that the interference pattern is restored. Erasing the path information works, which is why the experiment is called quantum eraser. I will once again present the homemade version of the experiment below. We shoot a laser beam through the slits again. A vertical polarizer covers the right slit, and the horizontal polarizer covers the left one, just like before. However, this time we insert another polarizer between the double slit and the screen. This will be the eraser. It is a polarizer set at a 45-degree angle. When we measure the polarization of the photons hitting the screen, we always obtain photons polarized at a 45-degree angle. Therefore, we cannot determine whether the photon originally passed through the left slit or the right one. As shown in the image, we obtain a beautiful interference pattern as a result. If we continuously approach the angle of the polarizer to the vertical direction, the interference pattern obtained on the screen gradually disappears. In another case, if we move the screen in front of the slanted polarizer, the interference also ceases. This proves that the phenomenon is not caused by the measuring device or the interaction between particles, because those effects cannot be erased. Moving the screen does not change those effects, but the obtained pattern still changes. Well, this experiment and its various versions have been performed numerous times in various ways, and the result has always been the same. If the particle's path is known, there is no interference. But if it is unknown, and multiple possible paths across different slits are possible, then interference occurs. Therefore, it is the information itself that is crucial. So far, no one has found an explanation for this, not even at the conceptual level. It seems as if we can go back in time and erase the past. Let's see the solution I propose. In my opinion, the solution to these mostly century-old problems can be summed up in a single word: wormholes. Why? I will explain that a little later, but first let's take a look at what a wormhole is. On a piece of paper, mark points A and B 20 centimeters apart from each other. If we fold the paper in a way that the points coincide in three-dimensional space, we end up with just a single point. Therefore, while the distance between the points in the two-dimensional plane is 20 centimeters, in three-dimensional space it is 0, as the 2 points become one and the same. The scientific name for a wormhole is Einstein-Rosen Bridge. if we want to create wormholes in three-dimensional space. We can only do so in a higher dimensional space. There must exist at least one extra dimension, besides the time dimension. But is such a dimension real? According to the general theory of relativity, the Sun curves the space around it. This was confirmed during a total solar eclipse by measuring the apparent positions of stars near the edge of the Sun and finding that they didn't appear where they actually were. John Archibald Wheeler famously summed it up as follows: matter tells space how to curve, and space tells matter how to move. So essentially, the Earth travels in a straight line at a constant speed along its own orbit around the Sun, but this path is curved because the Sun has curved it. It's similar to a race car driver going through a turn without having to steer left or right, but still continuing straight ahead because the turn is heavily banked. A straight line is a one-dimensional object characterized by a single vector. However, it becomes two-dimensional when we bend it. Similarly, a plane is two-dimensional, but it becomes a three-dimensional object when we crumple it. By analogy, a cube is three-dimensional, but if we curve it, we should obtain an object of a higher dimension. However, this extra dimension is very different from the others and is not the same as the time dimension. To perform calculations, for example, we need to use complex numbers. Therefore, I will refer to it as complex spacetime. It is also evidence of the existence of the extra dimension that in Dirac's equation, which is the equivalent of the Schrödinger's equation for high speeds, we have to use vectors with four components. A photon, which is just starting from the Sun, travels for more than 8 minutes to reach my eye. Currently, this would take over 2 years for our fastest spaceship. However, if we had a spacecraft as fast as a proton accelerated in the LHC, it would take less than a second for the astronaut. From our perspective, of course it would still be more than 8 minutes. The astronaut's own time can be calculated using Lorentz formula. However, the photon is even faster than this proton, so if we could see its own clock, it would show exactly zero elapsed time. Time stops for the photon. Therefore, for the photon, the moment it exits the Sun is the same as the moment it reaches my eye. The fact that these are simultaneous events is something all physicists know and accept. Now let's see my own assumption. Motion can only occur in time. No time, no motion. So every point on the photon's path represents the same location from the perspective of the photon. Therefore, this is a wormhole then. Well, I believe this is the assumption that solves the problem of the two-slit experiments. As we have seen, according to Richard Feynman, the double-slit experiments contain all the mysteries of quantum physics. Therefore, if we solve these, we will have a much easier time with the rest. We will see that indeed wormholes offer simple solutions to the other problems as well. Based on the above, the solution to the double-slit experiment is that all possible paths of the photon are individual open wormholes from which it randomly selects one. For every point on its path, it is the same point in both time and space. On the figures, I indicate the open wormholes with red wavy lines. Although I draw these wavy lines in a plane, it is more accurate to think of them as a complex dimensional spiral lines. They are wavy because the particle also curves the space-time just as the Sun curves it around itself. In this curved space-time, its trajectory becomes curved everywhere it exists, that is everywhere the wormhole is open. I will use two examples from the Macroworld. In the first one, a ship represents the particle which floats on the waves of the sea, that is the waves of the space-time. If both slits are open, then space-time ripples through both slits, thus interfering, and the ship floats on the stormy sea. In the second example, the person sitting in the train will be the particle, the switches represent the slits, and the rails will show the possible wormholes. If only one slit is open, it's like when the sea is calm. There are no big waves. The target is clear, and we have a good chance of reaching it. As you can see, there is no interference. The train easily reaches the destination. The reason for no interference is that the possible tracks do not intersect. However, this is not entirely true. The slit is never point-like. In the animation of the University of Colorado, on the left image the diameter of the slit is minimized, so it scatters quite a bit, resulting in a large spot on the screen, but with little interference pattern. On the right side, the diameter is wider, so it scatters less, resulting in a smaller spot, but with many more interference fringes. The explanation is shown below. The more point-like the slit is, the more direction the particle can take, and the wormholes barely intersect. With a wider slit, many more intersections are possible, leading to many more interference fringes. If both slits are open, then the open wormholes extend through both of them, intersecting each other, and thus the space-time waves beneath them interfere. The crests and troughs of the waves reinforce each other, just like in a stormy sea, making it easy to mistake the intended city, and other destinations come into play. Let's examine the solution to the double-slit experiment. As mentioned earlier, the red wavelines represent the particle's possible paths, which are also open wormholes. These locations represent the same moment in time for the particle, in other words, simultaneous events. If the paths arrive at a specific point from different directions, then the space-time waves beneath them also come from different directions, causing interference. Through the following example in the Macroworld, everything will become clearer, I believe. Imagine you are traveling on a train. This is a special train that can instantly be ready to travel any direction, and the ground beneath it is undulating. When you board the train, you immediately fall asleep. Later, when you wake up, you have no idea how much time has passed, where you are. Your watch has stopped, and it is pitch black outside. You might have just started the journey, but you could be here, there, or anywhere. You ask yourself, is it possible to arrive at the same point from different directions? If it is possible, it will cause interference, and that's why you cannot determine exactly which city you will arrive at in the end. If the answer is no, then the waves cannot collide, and therefore no interference can occur, making the destination clear. We can also say that you draw all possible paths and see if there are any points of intersection. This path information is what determines whether an interference pattern will form or not. The next case is when we peak. You remember, right? If we cover one slit with a vertical polarizer and the other with a horizontal one, the interference pattern disappears. Continuing with the previous example, let's say when you wake up, you encounter the conductor who happens to be a man. However, you know for sure that on the left city line all conductors are men, while on the right side all conductors are women. Therefore, you immediately know that you must have come through the left slit, and you are traveling to the left city. You know that the paths cannot intersect, so no interference can occur. The target is clear. The same scenario unfolds when you encounter a female conductor, but then you know you are on the other line heading to the right city. In this experiment, a given piece of information astonishingly changes the outcome of the experiment. Someone whispers something in your ear, and this completely alters the pattern on the screen. However, this is not only a characteristic of this experiment or even just a feature of quantum physics. Famous scientists themselves were skeptical about the Monty hole paradox. I must admit I also fell into the trap initially. In a quiz game, there are 10 doors and one of them contains the prize, a car. The player plays well, and eventually only 3 doors remain, one of which might have the car, as the empty ones need to be opened. Then the quizmaster assists the player by asking which door the player thinks the car is in. As a helping hand, the quizmaster opens another empty door and offers the player the chance to change his initial choice. If you were the player, would you move to the other door or stick with your first choice? I think I've already revealed the punchline earlier. The answer is yes. You should change your choice, as with the other door you have twice the chance. When the host whispers in your ear about an empty door, a machine that draws probability distribution functions on a screen paints a completely new picture. Naturally, the only information that matters is what the particle itself knows. The most intriguing case is that of the quantum eraser. If you recall, we inserted another polarizer, this time at an angle between the double slit and the screen. This restored the interference. The previous example still works with this case as well. Let's continue from the point where you meet the conductor. Since he is a man, you are convinced that you are heading to the left city. There is no interference and you reach your destination smoothly. You take out your mobile phone and start reading the news. You can only read yesterday's news because there is no network and time has stopped for you anyway. You come across a news article stating that starting from today a new rule has come into effect, allowing both men and women to work as conductors on both lines. This changes everything. The rays can intersect, causing the waves to interfere. Due to the interference, you cannot determine which city you will ultimately arrive at. The solution vividly demonstrates that the particle does not travel back in time. Any point on its path represents the same moment in time for it, but we perceive them as different moments. We perceive it as if the photon passed through the slits earlier, and we erase the information later, but for the photon these are simultaneous events. When the polarizer is rotated to a vertical position in front of the screen, a single spot without interference is obtained, similar to the single-slit experiment. However, if the polarizer is rotated to the 72-degree angle shown in the image, faint interference fringes appear because 90% of the photons hitting the screen have passed through the left slit and only 10% through the other slit, based on what we know about polarizers. Unfortunately, I cannot support this with a photograph, as it would require better tools. Therefore, I only draw the result here. In our example, the appropriate scenario is as follows. We meet the conductor who is a man. We know that out of 10 conductors on the left line, 9 are men and only 1 is a woman. Based on this information, we have a good chance of going to the left city and only a small chance of going elsewhere. This example clearly illustrates that only the information matters, not the interaction between particles or the measurement device. The reason is that we don't know what form the particles existing in the extra dimension actually exist. Therefore, everything is just a probabilistic event for us that happens in that dimension. I think it works in a way that out of numerous wormholes opening up, the particle randomly selects one through which it eventually travels. The experiment implies that the polarizers keep the wormhole open. They do not close it off, so they do not count as measurements. They only alter the properties of the wormholes, not those of the particles. Hence, it is possible that by seemingly introducing another obstacle, we actually allow more particles to pass through the system than before. In the left image, the perpendicular polarizers do not transmit light. On the right, we observe that with the inclined polarizer inserted between them, the background becomes visible, albeit faintly. All right, you might say, so far so good, but what about other particles, like electrons or buckyballs? Each has its own internal clock that keeps ticking, yet produces the same result. Let us first consider Bohr's atomic model. The electron's energy is quantized, meaning it can only occupy certain energy levels and not any value in between. When an electron emits a photon, it jumps to a lower energy level. But if it absorbs one, it moves to a higher level. If we perform a measurement, we can only find the electron on one of these energy levels and nowhere else. Physicists call this a quantum leap, although they don't mean it literally. However, based on what we have discussed earlier, we can infer that a quantum leap is nothing more than a jump through a wormhole. The double-slit experiment works with electrons as well, because the electron's clock also stops inside the wormhole. Our time does not stop while the electron jumps from one orbit to another. This has already been demonstrated. Next is the phenomenon of quantum tunneling. If we place many particles in a box and seal it, sooner or later we will find some particles outside the box. It is as if a prisoner digs a tunnel and successfully escapes through it. Once again, the physicists named it quite accurately, but they explained the phenomenon quite differently. In my opinion, quantum tunneling is just another name for the wormhole. We have the hammer, so we see everything as nails. For a photon traveling at the speed of light, its entire trajectory is a single wormhole. It remains in the extra dimension, much like a seaplane that is only in the three-dimensional world during takeoff and landing. You may argue that you see sunlight filtering through trees, for example. However, you don't actually see it because you only observe photons that have changed their direction due to interacting with tiny dust particles that act as tiny mirrors. For instance, you don't see the rays of the sun as they travel toward the moon, because there is no air in space, and thus no tiny mirrors. An electron, or a very fast spaceship, moves slower than the speed of light, so its wormholes regularly open and close, similarly to a motorboat bouncing on the water. Every time a particle's wormhole opens, its internal clock stops. But when the wormhole closes, its clock immediately jumps to the correct time following the Lorentz formula. We can also say that at this point it becomes real in three-dimensional space because it suddenly acquires its space and time coordinates like a GPS that finally receives the signal. The particle cannot go back to an earlier point in time. Space-time oscillates beneath the open wormholes. A larger object, like a buckyball or a large ship, operates in the same way as an electron. but its wormholes open and close so frequently that it becomes imperceptible to us, and thus we perceive it as continuous. So the movement feels continuous in the same way as when we watch a film. But this is an illusion. We only see images. We are only alive when we are in three-dimensional space. Our time stops in the extra dimension and we don't perceive anything. We only see different frames, but our brain stitches them together and perceives them as a movement. Therefore, each of us has our own frame per second rhythm. The idea is not new at all. More than 2000 years ago, Zeno and his teacher were already told, motion is only an illusion. We call it the paradox of the arrow. We may see the arrow here, there, or over there, but we never see it in motion. We never see it as it is moving. Now let's consider the mystery of quantum entanglement. When we shoot a laser beam at certain crystals, we occasionally obtain entangled photons as a result. For example, if we measure the polarization of one member of an entangled pair, the measurement of the other member will yield a result that is the exact opposite with 100% certainty instantly, regardless of their separation distance, even faster than the speed of light. A debate arose between Niels Bohr and Albert Einstein regarding this phenomenon. Bohr believed that photons do not exist as particles until the measurement takes place. They only become real at the moment of measurement. This is known as the Copenhagen interpretation. However, Einstein argued that everything is predetermined from the moment of separation, and hidden variables persist until the moment of measurement. Similarly to an apple that is bitten into, then cut in half, and the halves are sent to two different cities. When someone in one city receives the intact half of the apple, they immediately know that their partner in the other city received the already bitten half, no matter the distance. While they were alive, they could not decide who was right. In 1964, Bell devised an experiment that has been conducted many times since. Based on the results, hidden variables cannot exist. So nowadays it is widely accepted that Bohr was right and Einstein was mistaken. However, according to our theory, this is a Y-shaped wormhole. So there is no such thing as before or after, because for the photon these are simultaneous events. The moment of separation and the moment of measurement are identical. Therefore, both of them were correct in their assertions. The experiment can be performed with entangled electrons or other entangled particle pairs, proving that they are also within wormholes. Schrödinger's cat and a radioactive atom are inside a sealed box, along with a bottle containing poison. If the atom decays, it breaks the bottle, and the poison kills the cat. According to the current viewpoint, as long as no measurement is made, the cat is simultaneously both dead and alive. The act of measurement itself causes the cat to either die or survive. Physicists say that the wave function collapses upon measurement, ending the state of superposition and landing in one of the possible states. This is very different from what we are accustomed to, as we either see the cat as dead or alive, but never both simultaneously. Applying our new theory, the cat's wormhole closes spontaneously and frequently, not just as a result of measurement. Therefore, when we integrate the cat into the system with the atom, they have a single shared wormhole that closes both when we perform a measurement and when the cat's wormhole closes by itself. Thus, in this integrated system, the cat will never exist as both alive and dead, for a longer period than at any other time. Therefore, the moon is exactly in the same place even when no one is observing it. On this slide, we see what the currently used expressions mean in the new theory. You can skip this part if you wish. When physicists say quantum field, we mean extra dimension. When they say the particle is the excitation of a quantum field, it means wormhole for us. The wave function of a particle means a set of open wormholes above waving space-time. To find a particle at a specific location is a probabilistic event. The reason for this is the particle exists in complex spacetime, but we can make measurements only in real spacetime. The wave function collapses means that the particle's wormhole closes. This may be caused by the measurement, but it can also happen spontaneously. A superposition state means that the particle's wormhole is open. Electron cloud means the set of its wormholes. When we speak about stationary waves in quantum mechanics, it is because from the point of view of the particle, there is no time, there is no motion as long as its wormhole is open, so the waves of complex spacetime are stationary waves. Heisenberg's uncertainty principle is true because until the particle is in the open wormhole, we do not know precisely where it is. When we measure where it is, we close the wormhole, and a brand new one opens, but we don't know the exact direction. The reason for the Pauli exclusion principle is that any number of particles can coexist in the extra dimension simultaneously, but not in 3D. The next mystery is the Mach-Zehnder interferometer, also known as the quantum bomb. I will briefly explain it as there are many informative videos available on YouTube if you are interested in more details. When we send photons one by one into the system shown on the slide, due to the beam splitter the photon may end up in the upper pass or in the lower pass, reaching the detector labeled as A. It always reaches A and never B. If we place another detector or bump at the location shown on the slide, the following result occurs. If the photon hits the bump, it explodes and the experiment is over. However, if the photon travels through the lower path, our detector labeled B will occasionally signal, not just A. Therefore, in some cases when our B detector signals, we can tell that there is a bomb in the system without actually detonating it. I will demonstrate the solution using an apple, similarly to how I did with entangled particle pairs. If there were entangled particle pairs, then one member of the twin pair would travel through the upper path, while the other would take the lower path. However, the beam splitter cannot cut the apple in half, only keep it whole. This means that one member of the twin pair receives everything, becoming the whole apple, while the other receives nothing, becoming the empty apple. When the twin pair reunites, it continues its path in the corresponding direction from where it originated. If it came from the left to right, it continues from the left to right, thus arriving at the detector labeled A with a 100% chance. But if it came from top to bottom, it would definitely reach the detector labeled V. Now let's see what happens when we place the bomb in the upper path. In the case where the particle reaches the bomb, it explodes and the experiment ends. However, if we measure the empty apple, meaning we do not detect anything, it still counts as a measurement, just like when we measure the spin of one entangled particle and instantaneously know the spin of the other. Therefore, in this case as well, the other branch of the T-shaped wormhole closes, just like in the case of entangled pairs, and a brand new wormhole opens. In this new wormhole, our whole apple behaves as if it has just been a newborn, having no memories, so it no longer remembers where it came from, and it is no longer a member of the twin pair. Hence, at the next beam splitter, it can choose either the A or B detector with equal probability. Ultimately, the difference between whether there is a bomb that didn't explode or if there is no bomb at all, that a bomb can measure an empty photon as well, not just a real bomb. Now let's consider other experiments that could support either theory. In 1972, it was experimentally demonstrated that in a two-slit system, where only one slit was open at a time, interference still occurred. I believe this experiment supports the idea that a particle cannot originate as an excitation of a quantum field. Since only one slit is open at a time, the waves of the particle can either wave through the left slit or only through the right slit, but not through both simultaneously. We know that the particle can only interfere with itself and no other, so it should not cause interference. However, it does. The emphasis here is that the particle itself is a wave according to quantum field theory. According to our new theory, it is not the particle that waves, but the space-time itself. Therefore, space-time continues to ripple for a short while even after the slit has closed. It is similar to a ship suddenly lifting out of the water. If the ship generates waves in the water will continue to ripple for a while even after we have lifted the ship out. After one slit closes, the other slit immediately opens along with the new wormhole, allowing the formation of interference patterns. Another experiment involves conducting experiments with buckyballs. As mentioned before, from the two-slit experiment with electrons, we know that a particle can only interfere with itself and not with other particles. In the case of the experiment with buckyballs, several hundred or thousand different particles pass through the slits simultaneously. Since none of them can influence each other and can only interact with themselves, we should observe numerous different interference patterns on the screen if the particle is nothing more than an excitation of a quantum field. However, this is not the case as we only obtain a single wave pattern. This supports our theory, and let's go back to the example of the large ship. It doesn't matter how many lifeboats are on board, only the large ship generates waves in the water, not the lifeboats. The entire buckyball, including all its constituents, exists within the same single wormhole. The elementary particles within it do not have separate individual wormholes, so they cannot be independent and distinct excitations of a quantum field. We have already seen that photons remain in a single open wormhole throughout their entire journey. However, particles traveling slower than the speed of light regularly have their wormholes closed and a new one opened. If we insert a separator between the two slits, as shown in the figure, we can control whether an interference pattern will appear or not by appropriately adjusting its length. We know that if the length of the separator is 0, we will observe an interference pattern. But if it extends all the way to the screen, then we definitely won't see it. We can measure the length of the wormhole by gradually shortening the separator. The first appearance of the interference pattern on the screen indicates that the length of the separator matches precisely with the length of the wormhole. Currently, the widely accepted view is that the object's de Broglie wavelength, and the size of the slit determine whether an interference pattern can form or not. However, according to our new theory, the particle's velocity is the decisive factor as it determines the length of the wormhole. In the previous example, let's choose the length of the separator in a way that no interference pattern emerges, as shown in the left figure. Then we gradually increase the particle's velocity, and eventually the interference pattern must appear because the length of the wormholes will gradually increase. This implies that even though we humans can produce interference patterns, but we need to move at speeds close to the speed of light or fall into a black hole. What happens when a spacecraft flies toward a black hole? As it gets closer to the black hole, the gravitational attraction becomes stronger. Under the influence of this greater force, longer and longer wormholes open up. The last wormhole does not close at all. It remains open. Let's look at where the extra attraction force attributed to dark matter might come from. Let's assume that a GRB, a gamma-ray burst, hits two different stars, producing entangled atoms on them. Let their masses be m1 and m2. We want to calculate the gravitational attraction between the atom mass m1 and the capital M mass star. If entanglement did not exist, we would divide by the square of their center of mass distance in the formula. But we know that the atoms are in an entangled state. They exist within the same wormhole, resulting in zero distance between them. Therefore, we need to calculate with R2 instead of using R1, which is much smaller, significantly increasing the attractive force between them. Consequently, the stars attract each other with greater force, so we may call them entangled stars. Only the plasma of stars is capable of conserving a state of entanglement between them for a very long period of time. Let us continue with the evidence in the stars, which started on the previous slide. When a massive star explodes, and most of its material is shot into space in the form of gamma-ray bursts, in two thin beams, entangled atoms hit different stars, thus creating entangled stars. Due to their stronger gravitational attraction, the hit stars form a chain of stars. In the case of spiral galaxies, we see that the straight line of a previous gamma-ray burst is bent by rotation. In the next galaxy image, you can see how the entire chain of stars strives for the same orbital path. Eventually, they arrive in orbit, forming a ring-shaped galaxy. Below, you can see one of the main arguments for the new theory, providing an explanation for the formation of the most fascinating galaxy in the universe. Initially, it could have been a spherical elliptical galaxy where a gamma-ray burst occurred. The galaxy gradually flattened due to rotation, causing the line to break. Do you see how accurately we obtained the shape of the galaxy? Finally, you can see the galaxy's future in two other galaxy images. You can find more detailed explanations in these videos or by clicking on the portrait and subscribing to my channel. I'm truly grateful that you watched. Thank you very much.